Remember in our last lesson, what we did was to talk about the axioms for addition and multiplication. And what we'd like to do today is start looking at some theorems, and in fact, let's concentrate on some theorems with respect to addition, and then in our next lesson we can talk about some theorems with respect to the operation of multiplication, okay? And let's see how it goes. Rather than speak rather vaguely, somewhat vaguely about what a theorem is, let's actually look at one and see how the proof of that theorem goes, and then on the basis of that I think we can decide what is meant by a proof. Now let's see, suppose I were to, let me write the word theorem, and let me use the expression, the phraseology that we've been using thus far, and the symbolism for every A and B, all right, and C belonging to the set of real numbers. Now let's see what we can do. If A plus C is equal to B plus C, then what I would like to conclude, of course, is what? What is our statement, Doug?
A equals B.
A is equal to
B.
is equal to B. All right, and which this is our if phrase, is that right? Our hypothesis, and then this is our conclusion. And we would like to prove this statement. And after we prove it, in fact, we can then may call that a theorem. All right. So let's actually, let me write down the word proof, and the method by which we will prove most of our statements when we do so will be one that you are somewhat familiar with from either your work in Algebra 1 or else if you've taken geometry from your work in geometry, in which we will actually write down the word statement and reason for that statement, okay? And let's see how it might go. And here will be our first step of the theorem, of our proof of the theorem, and let's see what we may say, okay? Well, let's look at this, and A plus C is equal to B plus C will be our first step of our theorem, of our proof. And what might the reason for this be, Glenn? This is our hypothesis. This is what is actually given to us. And from this hypothesis, we would like to go ahead and try to prove the conclusion of the theorem. Is that right? Now, let's look at well, let me take A plus C. Now, we know that A is a real number and C is a real number, and when we add these two real numbers, we still have, what? A real number. Now, to this real number, what I'd like to do is to add another real number, which I'm going to call the opposite of C, all right? Now, if I took this number plus this number, is this still a real number? Will everyone agree with that? We still have a real number. And in fact, I think I may do the same thing with B plus C, and to that I would like to add the opposite of C. And do we still have a real number there? I think you will agree with that. And what is our reason for this one step? Let me include both of these statements in this one step. And we call this what, Doug?
The axiom of additive inverse.
Well, let's see. Not quite. Here, all I'm doing is taking any number x plus another number y, any two real numbers, and adding them. And as a result of that, we still get a real number, Doug?
Closure.
That then is still our closure property with respect to addition. Okay, let me use a little plus symbol to indicate addition. Now, the reason I wanted to include that step in here in step 2, this statement in step 2, is for us to be able to look at, let's say A plus C, and to that, I want to add the opposite of C, all right, as we have right here. Now, what I would like to do is to say that this is then going to be equal to, and I want to make a substitution. Give me another name for A plus C that we can see somewhere here. Oh, someone besides Doug. Bill?
B plus C.
B plus C. Right, there is a name right here for A plus C, namely B plus C. Let's then put in that name for A plus C, which is B plus C, and at the same time, I still have the opposite of C, all right? And what is our reason for saying this in this step here, Dick?
Substitution principle.
This is our substitution principle. Let me just abbreviate that. This is our substitution principle. And right there, I think you can see what direction the proof is going to go in, because let me then simply take this statement and rewrite it as A plus and C plus the opposite of C. Notice here I have some double parentheses. I could have used brackets. And here we have B plus, and then we have C plus the opposite of C. And what is our reason for going from step 3 to step 4, Don? That's our associative property with respect to the operation of addition, again, all right? And now let's look at that, and you say to yourself, I see a name for something in here. Here's C plus the opposite of C. Kirby? is 0. And here we have B plus, and C plus the opposite of C again is 0. And what is our reason for saying this? C plus the opposite of C is 0. Illustrates what property, or what property are we using there, Kirby?
Additive inverse.
That's our additive inverse axiom. Okay, very good. Our additive inverse axiom in order to be able to make this step. And then finally, let me put in 3 dots to indicate therefore A is equal to B. And what is our reason for saying this? A plus 0 is A. Brenda?
That's the additive identity.
This is our additive identity element. Okay, additive identity element, or identity element with respect to the operation of addition. Or another one, perhaps someone else might want to say.
The axiom of 0.
The axiom of 0, the addition property, or the addition axiom of 0, I think will be an equally valid reason. Okay, are we done? Have we proved what we wanted to prove? And looking at our conclusion, our last line here says A equals B, and from what we wanted to prove up here in the original statement, our conclusion that we wanted to prove is A equals B, and I think we'll all agree that we have. And notice we started from the hypothesis, and by a process of logical reasoning, based on, at this stage, all we had really are our axioms to rely on. Using our axioms that we already have, we then arrived at our conclusion. Now, every time we prove a statement, we then call it a theorem, and once we have that theorem, we can always use it, of course, to prove other theorems. And this is the process by which we will do this all year. Well, let's then look at, actually, if I were to take this original statement, let me write it again, let me use the word theorem. For every A and B and C belonging to the set of real numbers, now what I'd like to do, instead of writing it as A plus C, let me write C plus A. C plus A is equal to C plus B, then I think our conclusion will be still, Doug?
A equals B.
A is equal to B. And you look at this theorem, and the original theorem, the one over here in part A, and you say to yourself, well, all you can really do in one step, this is, in our second theorem here, it's a one-step proof, namely, to simply look at the first theorem and use what property? And Peter? The commutative property. And when we can prove a statement almost directly and immediately from a given theorem, we give that a name in our work, Doug?
Corollary.
That's called a corollary. C-O-R-O-L-L-A-R-Y. We call that a corollary. And what I'd like to do is to put these two theorems into one theorem, and in fact we can give that theorem a special name, because we'll be using it quite often. For every A and B and C belonging to the set of real numbers, if A plus C is equal to B plus C, or C plus A is equal to C plus B, then our conclusion is that what? A is equal to B. And the authors give this theorem a special name, and most other people give it the same name, Richard?
Cancellation property of addition.
This is our cancellation, C-A-N-C-E-L-L-A-T-I-O-N, our cancellation property of addition. Very good. All right. Now, we might also have a cancellation property with respect to the operation of multiplication. So if you simply say cancellation property, that isn't quite sufficient to identify it. So make sure that you realize that it's with respect to the operation of addition, as we have in this case. Very nice. Well, let's look at another theorem, and I think we can see how the proof of that one goes. Let me actually write the word theorem, because we like to prove this if we can. For every A and B belonging to the set of real numbers, all right, I'd like to talk about the opposite of A plus B. Now, again, from our work in algebra, in our first year algebra course, the opposite of A plus B, you know, is equal to, and Tim?
Opposite A plus.
The opposite of A plus
Opposite.
the opposite of B. All right, and now that's our conclusion that we would like to prove. And what name did we give this concept? It has something to do with the opposite of a sum. Is that right? The opposite of a sum. So if we had to give this particular theorem a name, let's just call it that, the opposite of a sum. And the opposite of A plus B, we know we would like to prove is equal to the opposite of A plus the opposite of B. Well, let's go ahead and prove it. Here's our proof in which we want to make a statement, and then we want to give a reason for that statement, all right? Now, perhaps it might require a little bit of background in order for us to be able to see what direction we want to go into as we try to prove some of these statements, all right? That's probably the one big distinction between an algebraic proof and a geometric proof. I think perhaps it's a little harder to see the direction in which one should go in an algebraic proof. It's perhaps not quite as obvious or as straightforward, at least in many cases. Well, let's see now. Suppose we had a plus b, all right, plus the opposite of a plus b. Now, think of this as x plus the opposite of x. And for every real number x, you know that x plus the opposite of x is equal to what? Is equal to 0. And what reason can we say this? Can we give for this? This is our, Bill?
Axiom of additive inverse.
This is our additive inverse, okay? Additive inverse axiom. Now, if we can take, say, the right-hand side of our original statement, well, let me then start out with a plus b plus, now let me write the opposite of a plus the opposite of b. If we can show that this statement is also going to be equal to what? What would you like to show? Is equal to 0. Is that right? Then you can say, well, look, in step 1 we have this is equal to 0, and then in step 2, if we can show that this then is equal to 0, our conclusion would be what with respect to the two left-hand sides in steps 1 and 2? What then can we say about those? Then, of course, they will be equal. Now look, let's think of them as being equal. If this were equal to this, all right, the theorem, the cancellation theorem that we just proved, and in fact that's the reason why I wanted to prove it today and for us to look at it, if x plus y is equal to x plus z, then what is your conclusion about y and z? They're equal by the cancellation property. All right? So that's the direction in which we're going to go, and you say to yourself, well, let's actually show that this then is going to be equal to 0, set these equal to each other, use the cancellation property, and you're done. Okay? And I think without perhaps a little bit of background and direction in which to go, some of these theorems might not be quite as obvious to prove as they could be. Well, let's see, I don't think I'm going to put in every gory detail here, but suppose I were to write a plus the opposite of a, in which I'm going to look at this, I'm going to use commutativity and associativity, and I think I can get to the point where I have there a plus the opposite of a, and then plus what? I think at the same time b plus the opposite of b. All right, again, notice the double parentheses. I could just as well have used some bracket symbols. What would then be our reasons for this? I think if you allow me in one step here to do all of this and give as our reasoning, what? Malcolm? All right, there we are using our commutative axiom with respect to addition and our associative axiom with respect to addition, and I think that would justify all of this. Now right here, rather than rewriting all this over again, let me simply indicate this is then equal to, and now we'd like to write another line here in which going from this line, what we'd like to do is to say this is equal to something. And of course, what then would you like to say this is equal to, Brenda?
0 plus 0.
0 plus 0. And a plus the opposite of a is equal to 0 is true for what reason? Doug?
Additive inverse.
That again is our additive inverse axiom, is that right? And of course 0 plus 0 we know is equal to, anyone is equal to 0. And what is our reason for this? For every real number a plus 0 is equal to a, where a happens to be the number 0, so Don?
The identity element.
The identity element for addition, all right? And perhaps to make it, let me then use axiom of 0 to be a little bit more explicit. Okay, this is still our identity element with respect to the operation of addition. Well, let's call that step 4, and then in step 5, our conclusion will be what? We have now from step 1 that this is equal to 0, and in step 2 down here to 4 that this is equal to 0. Therefore, what can we say? But that a plus b plus, and then we have the opposite of a plus b in step 1 must be equal to all of this. Is that right? Which is a plus b plus, and now let me put that in brackets, the opposite of a plus, I guess I put the brackets, the parentheses in the wrong place, but I think it's all right. And what's our reason for this? Brenda?
Transitivity.
This is our transitive property with respect to equality. Is that right? The transitive property of equality, the transitive axiom that we call of equality. All right, now, right here, in one step, what is our conclusion? What can we say? Brenda?
The opposite of the quantity A plus B
Therefore, the opposite of A plus B
is equal to the opposite of A
is equal to the opposite of A
plus the opposite of B.
plus the opposite of B. And our reasoning is, the reason for that is, Brenda?
Cancellation property.
This is our cancellation property of addition. Okay? Does everybody agree with that? And indeed, that's exactly what we wanted to show, and that's the conclusion of our theorem. And so you say, well, we're done. We've proved it. All right? Well, I don't think that there's much more that we need to do for today, so let me give you your homework assignment, and then tomorrow we'll look at some theorems about multiplication. So this will be a